Okay, so yesterday we talked a little bit about free fall and stuff, and I think actually when I got to thinking at the end, I think I left out the last page. Am I not? There was some stuff about like dropping a book and stuff, right? That I got thinking. I don't remember dropping a book yesterday.
No.
Yeah. So if I have time today, I'll do that little demo. I guess I could do it right now. Yeah. Okay, so you can write some of this down if you want. You can write all of it down. I wouldn't recommend you do that. Or you can sit back and enjoy, and you can print it out later or not. Entirely up to you. You're going to need them right away, Cole. Just relax. Okay, so a little bit of history about gravity. Gravity, of course, has always been there. It would be wrong to say that someone discovered it. You'd be more right in saying that Newton was the first to sort of explain it. And the classic story is that Newton got hit on the head with an apple. Probably didn't happen. If you do a little bit of reading, you'll find that during the Great Plague of 1665, the Black Death, the bubonic plague that was sweeping Europe, caused by rats and unsanitary conditions, people were dying left and right. They shut down the university. Newton was home from college, began thinking about gravity. The story is likely that he was walking through an orchard, an apple tree farm, and saw an apple fall, and noticed, you know how you can see the moon in the daytime, right? And knew that the moon, air quotes, fell down the edge of the sky, and he wondered, I wonder if the same force that causes the apple to fall is what's causing the moon to also fall in the sky. And of course he was right. Yes, it is gravity. Okay? So this all happened about 1665. A century before him, 100 years before that, a gentleman by the name of Dutch, I believe, Johann Kepler, maybe German, he had developed laws to explain the motion of the planets. So he observed the planets, which are the bright stars that you see in the sky and do not sort of wander, or they do wander throughout sort of the stars. They don't match a constellation or anything like that. And Kepler came up with these laws to describe the motion of them. And actually, those laws are still used today. They're commonly known as Kepler's laws. And they would put like the Earth at the center and the planets orbit in this sort of elliptical sort of path. And Newton's laws have something to do with the amount of area, that sort of like a pie-shaped kind of area, amount is swept out. And he noted that they travel faster in certain portions of the sky than others. Anyways, you guys don't need to know that. So Newton wondered if the same force caused an apple to fall to the ground from a tree. Okay, so blah, 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 skip a bunch of stuff. Newton came up with what he called the law of universal gravitation, which says, between every two objects there exists a force of attraction, and this force is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Blah, 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 nobody cares. Maybe not so much in this room. Others do. You might say you do, but you don't. I think I went through the whole I'm attracted to the filing cabinet, I'm attracted to the pencil sharpener thing, right?
Yeah.
Okay. So between any two objects, there exists a force of attraction, right? How much is that force between me and the pencil sharpener? Not that much. As I get farther away, it's even less, right? And so big G is known as the universal gravitational constant, 6.67 times 10 to the minus 31, I believe. In other words, 0.000000030 zeros, 67 times the mass 1, that would be the first object, mass 2 would be the second one, and r squared is the radius or the distance between them. In other words, big objects have a greater gravitational pull, and the farther apart they are, the less they get, the less the force of attraction is. All you really need to know is between every two objects there exists a force of attraction. All of this is sort of grade 12. Okay? Only thing you need to know is that between every two objects there exists a force of gravity. Why do things fall on Earth? Why does the apple fall to the Earth? Because the Earth has a gravitational pull. And now, just like I mentioned the other day, the force of attraction between, I don't have it out, but force of attraction between the moon and the Earth, right? How much is that force of attraction? Equal, right? The amount of attraction this way is the same as that way. It's the moon's gravitational pull that pulls the water and creates the tides on Earth. That's what we kind of talked about a little bit yesterday. Okay. Now, here's some stuff. Whoops, that's not what I want to do. Here's some stuff you probably should jot down. Say again? No, high tide is not always at night. The moon can be there, right? At night or at day during the day, right? It happens every 12 hours, right? Isn't it? Yeah. It always is. This is a term you should know. The region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. Okay? So around my big desk there at the front, it's fairly massive. It has a larger gravitational field than the gravitational field of, say, the pencil sharp. Or, say, Brandon's own gravitational field. Jeff is in Brandon's gravitational field. He can't, and if he's like anywhere near you, turns out you're in his gravitational field as well. Which one is a stronger gravitational field? They're pretty equal, right? They're of similar mass, maybe a slight difference, right? The gravitational field difference between the desk and the pencil sharpener is dramatic, right? But all of them you all have your own gravitational field as well. And the strength of the field in any place is defined as the gravitational force that a unit mass, a single kilogram, would experience if placed there. And it's represented by the letter G, and it's measured in newtons per kilogram. I'll pause. Here is a diagram of the Earth's gravitational field. And I don't know if you can see it there or not, because those lines are kind of light. I should redraw them for you. You'll notice that all the arrows point towards the Earth because that's the direction of the gravitational field, right? And where are the lines closer together? Where are the lines closer together here, Brandon? Close to the Earth, far away from the Earth? Close, right? In here, they're close together. It's stronger. Up here, far away,
it's not stronger.
It's not stronger. It's weaker. It's the density, it's the how close the lines are together that determines the strength of the gravitational field. Now, if somehow some James Bond supervillain was able to, I don't know, double the Earth's gravitational field, we would all weigh twice as much, by the way, right? And what would the Earth's gravitational field look like if it was twice as much? Would they be twice as long, these lines? That's true. It'd be twice as close together, right? So there would in fact be more of them. Right? That's what it would look like. I don't know how a supervillain would do that.
Yeah, probably.
Well, you'd weigh like 300 and some pounds.
It was like you feel like you're
Wouldn't kill you. It would probably cause your heart to work a whole lot harder, right? Like, you'd probably have a heart attack.
The moon would come and crash it.
Oh yeah, and then there'd be that too. And all those satellites too become. Yeah.
All those satellites would become.
Other than that, we'd be okay.
So it's survivable, that's what I'm hearing.
Yeah, it's on the ground.
So it's survivable.
So what you're saying is, I should try this.
You'd have to go on like some insane like diet to be like 50 pounds, like
50
be like 100 pounds, like drop all your weights, cut all your weights, then you'd be like 100 pounds.
It was like just a supposed fictional. How we got into that? Anyways, now this diagram implies that gravity is weaker as you climb in altitude. Okay? So as you go higher up, gravity is less. Now, you guys are probably way too young to know this, but in 1968, the Olympics were held in Mexico City. Yeah, the year I was born.
A bunch of world records were set that.
A bunch of world records were set that year in Mexico City. Now, is it because of gravity or is it because of thin air?
Thin air.
Both. A little bit of both, right? Gravity is slightly less in Mexico City, not enough that the average person would know it because you're farther away from the center of the Earth. you're farther away from the main mass of the Earth. Now, I've been to Mexico City. There's another city just outside Mexico City called Puebla, which is actually higher than Mexico City. Just walking down the street that day, I was winded. And I was like your age, year older, I guess, right? So physical exertion at that height is significant. When they climb,
That's why athletes go up in like mountains to train.
it forces them to become more cardiovascular, yes.
Wait,
Yeah.
you was our age in 68?
No. 86.
Oh!
No. I was born in 68. Yeah. Okay, but that leads me into this next statement. Okay? That leads me into this next statement here. And you probably don't need to sort of create this graph or anything, but yeah, they are. A graph of gravity at different altitudes would appear something like this. As you increase in altitude, what happens to the amount of gravity? It goes down. That's called an inverse proportion. Remember that word?
Yeah.
Inverse proportion. As gravity goes up, you would say gravity is inversely proportional to the altitude.
No.
Now,
No.
this particular point right here, like right at Earth, if this is 0, right at Earth, gravity would be like at, I guess that says 10, but it would really be like 9.8. Right? 9.8. I just wrote it for. Okay, this point right here is at 400 kilometers up. 400 kilometers up, about the height, the altitude of a space station. Gravity is about 9.5. So what's going on here? I've seen videos, you've seen Chris Hadfield, the Canadian astronaut, at an altitude of about 400 kilometers, gravity still pulls at about 9.5 newtons per kilogram. So instead of me weighing like 800, I'd be like 790. Hardly noticeable at all. Most people think, Jordan, you should be listening to this because this is going to appear on the test. Me explaining, if you miss a part, you're not going to understand the next part because you haven't got this one. Aren't space shuttle astronauts experiencing weightlessness? Didn't we see Chris Hadfield with the microphone letting it just sort of hang there, right? Weightless?
Yeah.
I just finished saying that the gravity at the space station is about 9.5. So what is going on? How can they be weightless but still have a gravitational pull of 9.5? Oh, I am. And you have to wonder what's causing that space station to orbit the Earth. Gravity. So there's still gravity there. So how come they appear?
Gravity's like not pulling down, it's pulling around.
Because it's in the point of equilibrium of the...
Here's the space station. Here's the Earth. Gravity is pulling it down. It's not pulling it sideways. Remember, we go back to this diagram, right? It's pulling it down, right? The gravitational force is between them. What is going on here? Okay, here's the key term. I would suggest you not write this down. Just sit and listen. If you want me to leave it up for a bit, I can do that. Okay? So, here's the key idea. The space shuttle astronauts and anything else in orbit are actually falling forever. They are in free fall, just like my book and my piece of paper. Brandon's brand new pencil when you drop it. Free fall. But when I borrow the pencil, when you drop the pencil, it just falls straight down. What's the difference? I'll use an eraser. No, I'll use a tennis ball. What's the difference between the tennis ball just dropping and the International Space Station? Huge, huge difference. Besides the fact that one's way bigger than the other. Like if I just drop it, it goes straight down.
It wants to keep going sideways.
Exactly. If I throw it sideways, it ain't going to catch it. If I throw it sideways, it not only keeps going, but it also falls down. Why does it fall down? Go ahead. Because of gravity. Right? As he throws it, it's going sideways, and it's going down. And if Zane could throw it hard enough, I'm going to draw the picture. Wasn't a challenge. If he could throw it hard enough, if he could stand on a really tall building up there, right, and he threw it sideways, and gravity pulled it down, well, where would it end up? It'd end up going like that, right? And then eventually it would go like this, right? But if he could throw it hard enough, it could go literally kind of around the corner,
All around the world.
all the way around the world. If you could throw it hard enough, the number is about 8 kilometers per second. So thinking about throwing the tennis ball from here to say like to the Country Fest site in a second.
Right on.
As much as I have a lot of faith in Zane, it's going to happen. Okay? So the space shuttle is traveling at a great horizontal speed. If you add these vectors graphically, what do you end up with? You end up with this. It in orbit. Right? So it's going sideways, but also being pulled down. And if you can go fast enough, then by the time, like if there is down, like if it takes that long to fall down, but down's no longer there. Right? There it's going this way. Right? And by the time it gets to down here, well, it's around the corner kind of thing. And it just keeps on going and falling at the same time. It is a little tricky. Now, if I were to take my scale, let's say you strap on the scale to my shoes, you take me to the seniors high-rise. By the way, please don't do this. You take me to the seniors high-rise, what's it, like 10 stories roughly?
Yeah.
And I jump off, or you push me off, what's my weight going to be? Is it going to be 800 newtons? If me and the scale are falling at the same time, what's my weight going to be?
0.
0. I will be weightless. How long will I be weightless? About 3 seconds. But when Commander Hatfield and the Canadian astronauts and the other astronauts are up in space, how long does it take them to fall that far? Oh, a little while, but by the time they fall, there's no place to land. They just keep on falling. If you take me up in a plane, you take me up in a plane and you drop me out of the plane, I'm going to be in free fall for about maybe 25 minutes, depending on how high up I go. Right? I'll show you a video later. I don't know if I got time today or not. I'll show it to you. Right? Depending on how high you go, right? Let's say 8 minutes. Okay, let's say 8 minutes. I'm going to be weightless for 8 minutes. If I take my tennis ball and I jump out of the plane and I let it go, what does the tennis ball do?
It's not going to stay there for a lot longer.
Is it going to just fall with me?
Yeah. Yeah.
Due to air resistance, right? There's a video that I have with the Mythbusters where they actually jumped out of a plane with, they wanted to find out what the terminal velocity of a penny was. Turns out it's pretty close to a human, right? And yeah, you've seen that one? Yeah. Okay, so when you take the penny, he jumped out of the plane, did skydiving, let go of the pennies, and the pennies just kind of floated in his hand. How come? Because they're both all falling at the same speed. That's what's happening in the space shuttle. They are all falling. How long? Forever.
So if something had a really low terminal velocity on the space station, would it like move compared to them?
I guess it would. Well, remember, there's no air resistance up there either, right? So there really isn't a terminal velocity. They have to be going incredibly fast sideways. Okay? It's about, anyone know how long?
2 hours.
It's about 90 minutes, one orbit.
How do they accelerate that fast to get
Yeah, that's a great question. They got to get up to a really, really, really high speed. Remember that on Earth, we have to accelerate things where there's air resistance. Once you get up far enough, no air resistance, right? And so you don't need that much force. Every force goes into accelerating. No force is required for overcoming friction. So you only have to do it for a certain amount of time, right?
So all
Good
you have to
question.
do is stick to your rockets that have to start going, and there's nothing to slow you down, so it's just going to go at that speed.
Do they have to keep firing the rockets to keep going?
No, they have to go, so then once it's going,
Once it's going, it's going. Absolutely. They're just keep on going, right? Yeah. Now, about, I think it was in the late 80s, the Americans put up a space station called Skylab in the early 70s.
I don't think I charged for littering.
Yeah, it landed in Australia, I think in the mid 90s. Unfortunately, out in the outback where there wasn't anyone, I think they did get charged for littering or something silly like that. But the orbit actually degraded. It eventually sort of started losing some speed. It maybe ran into things or what have you, and it eventually did crash to the Earth. International Space Station, that's not going to happen. They've got enough rockets up there. They can send up stuff. They can, Lego it together, add some more rockets, put it back into orbit. It shouldn't be a problem. Okay, so the vector sum of the horizontal motion and gravity causes the shuttle to orbit at the Earth at high speed. Since gravity is constantly pulling on the astronauts, they are in constant free fall, which is what we call apparent weightlessness. So it's not that the astronauts don't have a weight up there. It's just that they're just like me jumping out of the high-rise. You can't weigh yourself when you're in free fall, because the object that you're using to measure yourself is also falling. Does that make sense? It is kind of weird, but that's what's happening. They are in constant free fall.
So when you're up in space, like actually in space, then you're just floating around. Or you
No, it's all. You think about Jupiter orbiting the sun. Does the sun have a gravitational field out there at that distance away?
Yeah.
Absolutely. That's what's keeping Jupiter in orbit. You can't escape gravity.
Well, so when
You
you're
can't. I shouldn't say it that way. You can't escape. You probably can't escape the sun's gravity. Is there a certain speed that you can go to overcome it? Yes, there is. But it will always exist. Right?
If the gravity of the sun is like so big,
Yeah.
and the other planets, why we are expected to not?
Why are we not pulled off? Okay, that's a really good question. Really good question. Junior's asking, I think.
yeah, why don't we?
Okay, so let me just draw a picture. Here's the sun, right? Here's the Earth, pretty tiny. Here's Junior. He's really big, right? The sun's gravity is a lot, but at the surface of the Earth, because it's so much closer, you are more attracted to the Earth than you are to the sun. Even if you jump, right? You're attracted to the sun, but the Earth is so close, it's right there. Right? Why is the Earth continue to orbit? Because it's already going. It's already going.
put something
What
close-
caused it to start going?
something close enough to the sun, just like
Yeah,
Okay, I don't know. It would be.
it would.
Jupiter's way bigger, right?
Than Earth? Oh yeah, many times.
So, shouldn't the gravity on this, like the sun's gravity, be like more?
On
Like,
Jupiter?
farther away?
Now, the field strength is the same, but because of Jupiter's greater mass, that force is greater. But remember, Jupiter is a lot farther away, right?
Yeah.
So it decreases that force because it's farther away.
It's like, if it's still pulling Jupiter, shouldn't it be like way stronger than just pull us into the sun?
No. But remember, we're still moving sideways,
I
right?
feel like we're getting gravity on the moon then. It's not much farther away from the sun.
The moon's a whole lot less because it's a whole lot smaller, right? It's a whole lot smaller.
And isn't that one of those four? It's just a big old rock.
Do we ever get close to the sun? Actually, we orbit. It's not a perfect circle. It's actually kind of an ellipse. That's how it causes the seasons. The seasons is the tilt of the Earth. Yeah, there's times of the year where we're close to the sun. It's minor, but it's minor. We're never going to get like really, really close. Okay. Now, I thought I did a pretty good job of explaining it, but here's the same thing by someone else with video. All right, so an orbiting astronaut would feel like, what'd you put? Yep. And I would agree with Olivia. It should be, when I do this, when I click here, it should be, if I click here, no, I don't want that.
Hey.
I don't want, right? I got it correct, but if I get it wrong, I'm going to go back here. Can I go back? How do I do this? I need to get it wrong, say my answer, get a video hint. Right. That's
Think about this for a moment. That's the feeling you get if you're going over the top of the roller coaster, going like, "Whoa," and then you're doing this the whole time you're orbiting the Earth. So,
Okay, so like Olivia said, I think the question really should be not about to take a huge dive, but in the process of taking that huge dive. Right? Still diving. Wow. Right? So I should fix that answer. You're right, Olivia. Okay, what'd you get for the second? Oh, I have to let you, right.
Yeah, come on.
Okay, I'll start at number 2. You guys answer it.
Alright, let's go.
What is the frame of reference?
I don't know. Again, this is my first time through these, so I think some of these questions need a little bit of editing.
In the frame of reference of the person.
Yeah, the frame of reference of the person. What would the person see?
Oh.
I guess. I don't know. I know what the answer is, but
Wait,
come on, Junior. A, B, C, D, E, or E?
it depends.
Well, then that's E. Does E not say it depends?
It's not, it depends on other, where the people are. Wait.
You're making his hair fall out.
One did, but. No. See it? No. Ah.
Fast enough and tripped, you could miss the Earth. But there's a big problem. First,
Okay.
you have to be going 8
So you have
kilometers
to
a
depends.
second. That's 18.
Well, not that fast, not that fast.
The old Henry computer.
Okay, back question number 3. When a satellite is orbiting the Earth, it doesn't hit the Earth because. When a satellite is orbiting the Earth, it doesn't hit the Earth because. And the question, the answer is, you guys are doing good. It's C. It would hit the Earth, but it keeps on missing. Let me show you the video that talks about that here. Number 3. I got to get it wrong.
Back and put you and the little satellite over the North Pole and consider North to be up. You're going to fall down and hit the Earth. You are actually moving sideways really fast. So when you fall down, you're going to miss. You're going to end up on the side of the Earth. Fall.
You're going to go around the corner, as I like to say. Okay. Which of the following object experiences the force of gravity? An apple falling off a tree, an apple hanging on a tree, a bullet fired from a gun, a bullet dropped from someone's hand, a rock sitting on the ground, or F, all of the above? There is. 6 to be
Well,
precise.
really, if you think about it, they're all under, they're all experienced.
So what is the answer?
It's all,
So you're saying F, Cole.
well, bro.
You haven't said anything yet, apparently.
They're all on.
Come on, man. Be brave.
Discover gravity. I fell on.
Pick an answer.
On the.
Yeah, all of the above.
No.
All of the above. Oh, you have to go right to the start? Okay. Oh, video. That's the first thing it says.
Have you ever been floating in a swimming pool, all comfy and warm, thinking, man, it'd be cool to be an astronaut. You could float out in outer space, look down at the Earth and everything. It'd be so neat.
Everything on Earth doesn't have to be moving. Right now, you experience the force of gravity. You're sitting still, right? Gravity's pulling you down. It's weighing you down.
I wish we were floating.
Don't let it get you down.
That'd be cool.
Actually, that's right.
If a ball is tossed up into the air like so, when does it not experience the force of gravity? On the way up? On the way down? At the top? On the way up and the way down? All of the above? None of the above? I don't know. It's very stressful. When does it not experience the force of gravity? Not experience. Cool. Public filter. Public filter. I was more talking about the language.
feel like at the top, you don't have to.
I didn't finish the word though, I believe I left out the.
You know what, Cole? Just say, I'm sorry, Mr. Bennett. I'll try to do better next time. That's probably the best response. There you go. Correct answer is, come on.
No way.
None. Why is there gravity when the ball's going up? Why is there gravity when the ball's going up? Because it's slowing down. It would keep going, you're absolutely right. There's gravity on the way up, it slows it down. What about right at the peak? Yeah, it's about to pull it down, right? It's not like gravity goes, oh, there's a ball in the air, I'm going to turn off for a second. Gravity is here all the time. 100%.
When you're jumping on a trampoline and you have your phone, when you're at
Yeah.
the peak and you let your phone go, it goes like at the same speed as you're going all the way down.
Yes, I would recommend trying it, but yeah.
When you're on a roller coaster?
If you were to let it go at the same time, it would, yeah.
So that's,
Yes, yeah.
one of the,
Yeah.
seems like a good idea. I'm skydiving, let it go. It's still-
I would suggest use a ball, not a phone. Okay, now, these ones aren't multiple choice. If an astronaut is orbiting the Earth, let's go of a rock. What will happen to the rock? Describe the path of the rock and why it follows that path. Here's Earth. Here's Junior the astronaut. And here's his rock, and he lets go. Well, guess what? Rock and Junior are both going to do what?
Sideways and down.
They're just going to keep on doing what? Orbiting. In a circle, right? Not all sort of crazy like this. But
It doesn't have a.
will the rock stay with him as he goes around?
Yeah.
Absolutely. Absolutely. In fact, when the astronauts go out on those spacewalks, they're hurtling through space at like very, very high speeds. They have to be careful that they don't run into space junk. What'll happen? There's like a little bolt that got right. Yeah, it'll go right through them. Okay. They are going. It looks like they're floating. They're hurtling through space at very high speeds.
If me of the other timeline, if I alone there,
Yeah.
just me and the ball.
Yeah.
Can I throw the ball? Or
Sure, you could throw the ball. Would the ball then stay with you? No, it would keep going. It would actually create, because you're throwing it, you're creating an even faster speed.
Or I have force?
It would join, yeah, you would have to force it to go. But what would happen is eventually you would be orbiting closer and the rock would be at a farther distance because it's gone farther. Not faster. Eventually it would take up an orbit that is, it might be elliptical. Uh-oh. It's not a phone, it's a clicker. They've been pretty good over the years. You know what, let's call it a day.